The final topic in this chapter is polarization. First, we're going to talk a little bit about what polarization actually is, and then in the next video we'll look at some specifics of polarizers. So the basic idea of polarization is that there's a given plane that we can define based on the alignment of our electric field in an electromagnetic wave. So we know that our electric field and our magnetic field must be perpendicular to one another and that both are perpendicular to the direction of propagation. However, given a direction of propagation, either you can have B in the Z direction and E in the Y direction, or B in the Y direction and E in the Z direction. In either of these cases, your direction of propagation is still in the X direction. Now obviously we can pick any rotation between these. I can have B, for instance, at a 45-degree angle, and then E would also be at a 45-degree angle. I mean, that works too. But fundamentally, we can have some plane that aligns with our electric field vectors, which then always point in that plane. So we would call this vertically polarized if our electric field is going up and down. Our magnetic field is then going horizontally. And we have horizontal polarization if our electric field is lying in the horizontal plane, then our magnetic field is in the vertical plane. So it's important to understand that some light is polarized. Naturally, lasers are polarized. They have a polarization plane. Radio antennas, as we talked about in the last video, also have a natural polarization orientation. Reflections are mostly polarized. It kind of depends on what it's reflecting off of. And there's an interesting phenomena that light scattering in the sky from the sun actually is partially polarized. But with that, it's a little trickier. This isn't as perfect of a polarized light as you would get from lasers and radio antennas. And so one picture here is that you have some sort of bowl of water with some rocks in the bottom, and the reason the surface looks kind of white is because of polarized light. Now in this case we have a polarizer, so we're looking at the light that's polarized horizontally, and it still looks very bright. We're seeing a lot of the light from the reflection. But if we then look at the same situation through a vertical polarizer that blocks the horizontally polarized light, which we're going to talk about very soon, and instead we now can see very clearly the rocks in the bottom. So reflections, again, are mostly polarized, and these are horizontally polarized. And so one of the most interesting applications of polarization is the idea of polarized sunglasses, which serve to block some of these reflections. Now, the important thing to recognize is that most light is actually unpolarized. And so in many situations, you're going to have to account for the unpolarized light before it enters your polarizer. Now, unpolarized light just means that it's a sum of light that comes in all possible polarization orientations. So it isn't to say that it has no alignment of the electric field. It's just that you can imagine little pieces of the light, or basically a sum of a bunch of waves where the electric fields are in just random orientations. So this is basically a sum of all possible polarizations, not that there's no electric field whatsoever. So we'll talk about that a little more soon. So finally, what we really deal with when we're talking about polarized light are polarization filters, or Polaroids is actually what this is. So this is a special type of plastic that basically has these long polymer chains, these long molecules that are partially conducting. So if you try to send through light this way that has an electric field that's up and down, it actually can't pass through because of the alignment of the polymers. However, light with an electric field orientation that's perpendicular will pass through. So every polarizer has an axis, and that is basically what orientation of electric field does it let through. And you can think of this as blocking the electric field that is perpendicular to the axis. So this is how we imagine our unpolarized light. It has electric field vectors in lots of different directions. It's a sum of many different waves that have different orientations. But after it's passed through the polarizer has only let through the components that align with the axis. So the polarizer basically reduces our intensity because it's blocked some of the light, but all of the light coming through an ideal polarizer aligns its electric field with the axis. So in the next video, we'll talk about this in some greater detail, and in class, we'll actually play a little bit with polarizers. These will just seem like kind of grayish plastic, but again, we see some interesting properties when we start interacting with light.